This is Elaine McCormick for Lab 5, Motion of Falling Objects. I observed a Band-Aid box falling, which falls quickly, and then I also observed a paper which falls slowly due to air resistance and drag force. The main result from this lab was to see how air resistance causes the objects to fall at different speeds. So, to do this, my main objectives were to compare the falling objects' velocities, find the terminal velocity if there is one, and look at the difference between air resistance to weight ratio of the object, which affects the drag force. So, my observations and video. The first video you see here is my Band-Aid box, which is my heavier object that falls rapidly. I put the video in Tracker. I cut the video so that the box is falling and in air during the whole time. It's about 0.4 seconds long. I used a calibration stick of 0.08 meters, which is the width of the Band-Aid box, as my length scale for the video, and then I set my axis so that it'll fall along the negative y-axis. And while it's doing that, you can see here that I recorded a point mass to record its position versus time to look at the velocity when I get my data. I also have my paper falling here, which is the same thing. It's about half a second long video. Set the length scale to 0.2 meters, which is the width of my paper, and then you can see it falling here on the negative y-axis, which I set with the point mass to record its position versus time. Okay, so once that's recorded and I've gotten my data from that, I made a model in VPython of these two things. So first we're going to look at the just gravity model, which represents my Band-Aid box, the object that falls quickly. I put in my initial conditions, which is the mass, and the velocity vector, which has no initial velocity because I'm just dropping it. And the forces acting on this object during the time are just gravity. So you see that here when I run it. There we go. Red arrows, gravity force. You can see the ball falls, and then it continues with increasing velocity throughout the whole time. And that's really important because when we compare to my model that includes the drag force, which represents my paper, it's going to look different. I still put in the same initial conditions. However, this time I included the drag force, which is proportional to the velocity in the opposite direction, so that the net force is the gravitational force in the negative y, and then the drag force in the positive y. You see the drag force represented by a blue arrow, and the gravity is again the red arrow. So there it goes. If you look at my graph, you can see it increases until it reaches a constant velocity due to the drag force. The two forces cancel out, the net force is 0, and it continues to fall at constant velocity. Note that during these videos, I made the time steps small so you can see it, and put them to run about the same time as my tracker models, so that when I come in here, you can see my gravity model versus my rapidly falling object, the Band-Aid box. You can see they line up and continue to increase throughout the time period. You can see the slope continues to increase, whereas when we look at my drag model, which is due to air resistance, we saw that in the forces, with the slowly falling object, it goes to a straight line because the velocity becomes constant due to the drag force equaling the gravitational force. So, moving forward, what does this mean? Hold on one second. Okay. When we use the slowly falling objects model to observe motion with and without drag force, so that's my paper, we saw that the drag force is proportional and opposite to the velocity. And when Newton's second law occurs, F net equals 0 when constant velocity, you reach the terminal velocity, which can only occur with drag. So we see here the model with drag reaches a terminal velocity and continues with constant velocity, due to the forces equaling each other and canceling out, so the pushes and pulls equal 0 on the object. Whereas without drag, we only have force in the negative direction, and so it continues to increase throughout the whole time. So, what if? I looked at a model with no initial velocity because I just dropped the objects, so we looked at comparing them with something with an initial velocity in the y direction. So we have my slow model first, with no initial velocity. You can see here, with drag, it has constant velocity, and then without drag, we have increasing velocity. Well, this doesn't change when we add initial velocity. However, if you see that the model with drag reaches its terminal velocity, which is when the velocity is constant, much quicker, and same thing for without drag, it just with added velocity initially, it increases the final velocity because you're just continuing to increase throughout the whole time. So that's what we found. Our overall results are that drag is related to terminal velocity because it is the reason for terminal velocity. Air resistance equals out with the gravitational force causing drag, causing terminal velocity. Velocity is related to the air resistance because it is a force acting on the object when it's falling along with gravity. When there is a constant velocity, a terminal velocity, the pushes and pulls equal 0, the F net equals 0, and you have a constant velocity. And a thing to note is that drag force is always opposite to the force of gravity in free fall, and is the reason that we get constant velocity in objects falling.